Hello, this is the third complex numbers video of OCR Pure Core AS Further Maths, and the title is Multiplying Complex Numbers. You may already be aware of two properties for operations, one being distributive and the other being commutative. In general, when we've dealt with real numbers, we've found that a brackets b plus c equals ab plus ac, and also that ab is the same as the product BA. We are used to the idea that multiplying by a scalar, i.e. a real number or constant term, you just multiply each term by that number. You are also used to multiplying two algebraic expressions together. If we are to multiply two complex numbers together, in effect we expand the brackets of the following expression. We can either do this via a grid method, which some of you may have used at GCSE, or by doing what we might call the FOIL method, where if you have, say for example, a plus y, b plus x, you do all these terms. So either of those two methods can be used for this one, for multiplying two complex numbers. Of course, you also need to remember that if square root of minus 1 equals I, then I squared will equal minus 1. So, expanding these brackets, we would get 8 plus 12i minus 2i minus 3i squared. If we gather up our real terms, what we get here is 8, and remembering that this expression here actually is the same as plus 3, so that's our real part, and then we also have 12 minus 2 lots of I, which would give us overall 11 plus 10i as our answer. You'll note that the product of two complex numbers is also a complex number. If we were to use the grid, doesn't matter which way we write this, but some of you may prefer this initially, you would see that we would fill it in just the same way, and then gather up terms afterwards. It may be worth just pointing out here that in general, if we use z to denote a complex number with real coefficients a and b, we may, when we multiply, write this as z1, a particular complex number, times another z2, or sometimes we use the letter w. And if we write them next to each other, that denotes a multiplication. Focusing on this idea of it being distributive, we can see here that if you have two lots of 4 minus I, you would have 8 minus 2i, which is in effect the equivalent to ab plus c equals ab plus ac, and that's the distributive part being confirmed. It's also worth considering here the powers of I. So let us just start with, we know that I is the square root of minus 1, and therefore the I squared equals minus 1. If we consider I cubed, it is therefore I times I squared, or in other words, minus I. Think about I to the 4. That would be I squared times I squared, which would equal minus 1 times minus 1 equals 1. Moving on then, some of you may already be ahead of me on this. I to the 5 will be I times I to the 4, which will be I times 1, back to I again. So you can see that it doesn't matter what powers of I may occur in the working when we're multiplying or doing anything else with complex numbers, we're still not going to be adding any additional numbers to the complex number system than I. Let's now consider expanding a complex number such as 2 plus I to the power of 3. You may want to pause to discuss this amongst yourselves or to consider this on your own for a little while before I start. If you choose to use the binomial expansion to help you do this, you might want to think of a Pascal's triangle of 1, 3, 3, 1 pattern. The fact that then you're going to be decreasing the powers of 2 and increasing the powers of I, and then pulling it all together. So for example, that first column will be 1 times 2 cubed times I to the 0, which in effect will also be 1, giving us an 8. The second column will be 3 times 2 squared, or in other words 12, and then you have it times I, and it is positive. In the third column you have 3 times 2 to the power 1, which would give us 6, and then I squared, which is minus 1, remember, so that would give us a minus 6. And finally 1 times 2 to the 0, which of course is 1 still, I cubed, which you know is minus I. If we gather those terms up together, we end up with 8 minus 6 for the real part, and 12 minus 1 for the imaginary part, giving us 2 plus 11i as our answer. If you prefer not to use the binomial expansion, you can of course just multiply out the brackets. So first of all, just work out what 2 plus I squared would be, and then that would be a quadratic, and then multiply by 2 plus I again. This is shown on the slide here. In this case, we've multiplied the first and second bracket to form that first quadratic. However, in I squared, of course, is minus 1, so that reduces down to 3 plus 4i, and then they've post-multiplied by 2 plus I. If you had decided to multiply the second and third bracket together first, then you would have ended up pre-multiplying by 2 plus I. Let's have a look at a slightly more interesting problem. Here we are given that z equals 2 minus square root 3 of I. We need to express z plus z squared in the form of a plus b root 3i, but a and b we're told, are integers. Let's have a look first of all at what z squared would be. So we've got 2 minus root 3i times 2 minus root 3i. It's probably worth writing this out in full to make sure you don't make any silly mistakes. You could also, of course, use the grid method. Well, that gives us 4 minus 4 root 3i minus 3. That 3, of course, has come from the fact that I've done root 3i times root 3i, which would give me 3i squared. And then, of course, the I squared becomes minus 1, so that's where I get my minus 3 from. We just put that in a bubble so you don't get confused. If I gather those terms together, 4 minus 3 is 1, and then I've still got my minus 4 root 3i. Note that I can write that quite happily as an integer times a third. If I then wish to add z plus z squared, all I'm adding is 2 minus root 3i. And again, I'm going to choose to put that in brackets, just to make sure that I don't make a mess of my signs. And the 1 minus 4 root 3i. Looking at the real parts then, that gives me 2 plus 1 is 3. And then I have minus 1 lot of root 3i, and then take away another 4 lot of root 3i, which gives me altogether minus 5 lots of root 3i. So in this case, Given that they wanted me to write this in this form, I might now also make it clear in my answer that I had found that A equaled 3 and that B equaled -5. In the next session 1.4, we will investigate how to divide complex numbers.